sublinear algorithms in adversarial environment.
Thank you. Yes, that's the alternative. The alternative title. Yeah, of course. I briefly considered. Okay, so the workshop is about extroverted sublinear algorithms, and I really took it literally. And this is where what I'm going to talk about. So I have background in security. I worked for quite a few years in differential privacy, and obviously everyone here cares about sublinear algorithms, sketching, and this is this talk. And I'm not kind of the focus of this talk. I'm not going to impart you with a lot of technical knowledge. My goal here is to share my enthusiasm for this particular space, for this particular set of problems. And okay, so we'll talk about the model. I'll cover a couple of problems in this model, and then then we talk about relaxations of this model, and finally I'll conclude with connections with differential privacy. Okay, so as like in streaming sketching, and by the way, like in this talk, I'll be kind of using these terms interchangeably. We often talk about worst case analysis, right? And why is and kind of this is the standard problem. Like we have some device that keeps track of a stream that goes by, wants to compute some function, and we say that like there's an adversary that provides the worst case input, but it so happens that we have a very reliable way, very kind of robust way of defending this against this adversary is randomness, right? So once this device has its own private randomness, then kind of this worst case input becomes the average case under kind of the probability space that's controlled by the device. But what if we move into a distributed setting? So, for example, Graham Motho and he proposed back in 2008 the model of distributed functional monitoring, where there are small sensors at the edges that are monitoring not the entire stream that passes by, but some fraction of it. Like some kind of, each observer has its own view of the stream. There is a central monitor who wants to compute some function of the stream that is shared, that is observed jointly by these edge devices. And so that's a kind of very inertial model. We back in the day we were motivated by a somewhat separate problem where the devices share files, and they gossip about these files, and they want to kind of update each other's state when they meet. But I like this model a bit better. It's more general. It's like easier to explain, and it's obvious what are the criteria that we're optimizing for. We want to minimize communication, the computation of the edge devices, like they're supposed to be weak, and of course we want the joint function that is computed by the monitor to be accurate. But what about the defense against the worst case adversary? So previously we said, well, kind of there's some randomness that that will transform the worst case into the average case. But if these edge devices, they need to share randomness, then the randomness effectively becomes public. Like it becomes much harder to argue that the randomness does not leak. And for this, I lean on the authority of Benjamin Franklin, who actually did say that 3 may keep a secret if 2 of them are dead. He may not be the first person who said it, but he kind of included in his For Research Almanac. So, and kind of the motivating example for the first part of the talk is going to be defense against the worst case, against the adversary who is able to craft the stream in response to the randomness that, or kind of the state that these devices share. And this gives rise to the adversarial sketch model that we introduced back in 2008, which is split between the sketch phase, where the inputs are chosen adversarially. There's no shared secret between devices that are trying to do a computation. They are not allowed to communicate. And then they switch to the interaction phase, but the only information that they retained from the input is the one that is encoded in the sketches. And in that model, we considered kind of very basic, like try to understand what can we do at all under these constraints. And the first problem that kind of comes to mind is equality testing. Whether the sets that the devices observe of bounded size, whether they are identical, and we want to bound the error probability. So in the setting of public randomness, the answer is well known. It's extremely efficient in the error. It's independent of the size, and also the computation and like all relevant properties of the algorithm are extremely are also very efficient. In the adversarial sketch model, the lower bound is actually quadratic in the size of the set. It's like dramatically worse than we can do with private randomness. And they have a matching upper, an upper bound that is like not exactly matching, but kind of roughly gets in the right ballpark. We then consider symmetric difference, where the goal is to approximate the difference between the sets, and like with somewhat similar, like or at least qualitatively similar results.
So in the adversarial sketch model, does the adversary see like multiple interactions between the users, or like how do they interact with the users to get their relative readiness?
So there's no interaction, or there's minimal. Like you'll see how it works. I'll kind of it's going to be pretty obvious. So where do we get the low bound? It comes from the simultaneous message model that was introduced by Yao in '79, and in this model, the two devices have separate inputs. They compute some sketches, some kind of smaller representation of these inputs, and then they simultaneously like share it with the party, with the third party who computes the function of these shorter inputs. And the low bound for the equality testing was proposed in 1996 and then kind of improved by or generalized by Kimball in '97. That was effectively what I stated on the previous slide. It was a roughly like the square root in the size of the sets whose size we are comparing. And if we go back to that, like to this algorithms, like to that algorithm, it's beautiful, and it's kind of in retrospect, it's very natural. So Alice and Bob, they apply error correcting code with a large relative distance 1 minus epsilon, and they write separately this error correcting code as a matrix. Yeah. It's the absolute distance divided by the length of the code. So they write out this code as a square matrix. And then Alice chooses a random row, Bob chooses a random column, and they send this random row and random column to the monitor, to the kind of the third party, who then compares, like looks up the entry at the intersection. And if the relative distance between if these two strings or sets, like there's like technicalities that we can resolve, if these two strings are different, then by the property of the relative distance, epsilon fraction, or 1 minus epsilon fraction of this entry is going to be different. Therefore, a random entry that is kind of indexed by a random row in the random column is going to be different, right? And this gives us immediately a low bound in the adversarial sketch model. But then there's a difficulty, which is that in the sketch model, these strings are given one by one, like one element at a time, or kind of by updates that are flying by. And if the relative distance is as high as y minus epsilon, and even though like Alice only has to maintain a random row in this matrix, in this error correcting code, it still has to update 1 minus epsilon fraction of the entries, right? And now, like, we started with the premise that these are weak devices that can store the entire stream, and yet we require them to first maintain the state of the size of the square root of the size of the dataset, or the length of the string, and then on every single update, we require them to do square root of k or n computation. And that sucks. Like, that's something that we don't like. And it looks like in an actual kind of abstraction that we kind of can get around, because the relative distance of 1 minus epsilon and kind of the low weight of the parity check matrix don't seem to be compatible. Either you get either one or the other. So like we sort of like are looking at the impossibility result, but I wouldn't be telling you that if we didn't have a way around it. So if we actually consider what we mean by the relative distance, we are looking at the relative Hamming distance, like the distance between the codes, like the Hamming distance between the codes divided by their length. So we kind of get around the impossibility result by considering a different distance metric, where the code is going to be actually a collection of codes of increasing sizes, and we'll be looking at kind of effectively we'll be assigning different weights to the distances in every to the Hamming distance in every code. So that was like a pretty neat idea. For the symmetric differences, it required like some more work. And let me kind of okay. So I'll be moving on from this kind of problems from this model. Any questions? Okay. So I offer an aside, which is about adversarially robust data structures, which is not related to stream and sketching, but kind of it's still roughly in the same in the same ballpark. So if we think about hash tables, then in retrospect, it's relatively easy to trigger like to the worst case behavior for hash tables by kind of forcing a lot of collisions. And how we learn about collisions by observing how hash tables react to kind of what we feed them. And indeed, this attack vector was described by Lipton and Norton back in 1993, and it was thoroughly forgotten until a paper by system security researchers who described an actual attack on Perl that was back in the day, was really kind of what held the internet together, and it had quite a bit of impact. Perl was patched and then it was thoroughly forgotten until in 2011, another set of security researchers, they attacked PHP, Java, and Python, and it required another round of patching to kind of get around this, like to replace these hash functions with something that is like typically has some internal randomness. Like I think that's kind of the path they decided to go. Then there is a line of work on robust boom filters, a bit closer to this crowd, and then I'll skip that. Okay, so so the lesson about our work on sketches in adversarial settings, it's a lesson for kind of people who are starting their careers. So the mistake that we made was that we described the problem and solved it, right? So then like there was pretty much nothing to do in that space, it was until Moritz and David, they came along and they realized that our model was a bit possibly way too strong. So their insight was that the traditional adversarial input model is too weak if the sketch is kind of acted upon before the stream's end. Our model, the adversarial setting model, is too strong because it presumes that there's no private randomness. But there are many instances where this assumption is not justified, where it's a single device that is allowed to maintain its private randomness. So we went overboard with strengthening our model. So what they say is that, well, the adversary is not blind, but it's not omniscient either. It can't read your mind, but it can react to what you output. And the motivating examples for that would be dynamic pricing. Like if you're monitoring your inventory and you're setting prices accordingly, if the inventory runs low, you raise prices, right? Then what you tell to the world will affect how the world interacts with your your backend. It can be machine learning. It's my current line of work, where it's all about the feedback. And in principle, any adaptive system where it interacts with the world will lead to some feedback loops, some entanglement between its internal state and what the world knows. And what the demonstrated in that paper, how robust are linear sketches to adaptive inputs, was a strong negative result to the hope that linear sketches can survive, can be robust under inputs that are adaptive to their output. And unfortunately, I don't have time to sketch their solution, but it is beautiful. It says it basically leverages the insight that each time linear sketch releases, we interact with the linear sketch, we learn something about the projected space. And by the way, that paper is also a evidence of the Betteridge law of headlines. Any headline that ends with a question mark can be answered with the word no. So if you see a question mark, you know the answer is going to be negative. Okay, so then a few years later, there was, so Omri is here, right? Yeah, Omri, yes. Beautiful paper. So it offered a very insightful, very encouraging positive result in a fairly restrictive model of insertion-only multiplicative approximation. And the insight of that paper was that in the insertion-only model, and multiplicative approximation, the count only goes up. If we are targeting multiplicative approximation to the current count, there are only so many discrete values that we'll ever need to output, as long as we want to be within a multiplicative approximation to where we are. And what they said is that we'll run key sketches at all times, but at any given time, only one sketch is going to be active. And that sketch is where we are. And once that sketch detects that we have to kind of jump to the next level, it does that and kind of kills itself. Like we use like a burner sketch. Once it's used, it's gone. But because of these constraints, we only need the algorithmic number of sketches, so we are good. Yeah. And then finally, I'm going for the punchline: adversarial robust sketches and differential privacy. And if you told me that like kind of there's a connection, I would tell you like a while back, get out. Can't possibly be a relationship because differential privacy is all about protecting individual kind of entries. And in sketching, individual entries kind of are a dime a dozen. Like that's kind of the name of the game. Like the data set is huge. And if it's fully under adversary's control, there's nothing that differential privacy is going to tell you. But that's a mistake because in this result, differential privacy is applied not to the inputs into the streaming algorithm, but to this logarithmic number of sketches themselves. So what they say is that kind of they use what's called the sparse vector technique, and instead of using this one sketch at a time, they'll keep computing the median between the sketches in a differentially private manner that protects the identity of the sketch that is like actually closest to the truth. So this is an instance of differential privacy doing something for algorithms, not the other way around. Okay, and I'm at time. So there are definitely kind of directions that I encourage everyone to pursue. Kind of the models can be refined, kind of splitting the difference between models inputs which are adaptive but not necessarily malicious. Sketches that can detect that that they're stopped cease being correct, but that once they kind of say, "Oh my God, kind of I'm being attacked," they don't have to maintain correctness. Kind of that would be a kind of useful device too. There are recent results that exploit computational hardness assumptions, basically crypto, and kind of just if you are thinking about the hard technical problem, then the adversarially robust sketches for the translator model would be an interesting one. Thank you.
Questions for you?
Do you have concrete examples? A concrete example where like you really need to use an adversarial robust sketch versus like a regular sketch will fail miserably.
Okay, so that's why I kind of used the examples from hash tables, where you absolutely have to, otherwise like the internet is going to melt down. For sketches, I think kind of like Hart and Woodruff paper, they talk about like high frequency trading, but I don't think we have like kind of obvious examples in the wild where it is strictly necessary.
So it seems like you were saying that adversary has a lot of power. You can assume that the adversary can sort of only change the alpha fraction of the stream or some limited amount of control over the input. Is there anything already studied or anything that's interesting?
Omri, do you have an answer?
It feels like robust statistics, right?
Sure, that's where I got the idea.
No, I don't know.
Okay. Absolutely. That would fall under this rubric of refining the model, of relaxing the model.
Further questions? Okay, so let's turn to Yakin.